This question from the chapter application of derivative. We are given a rectangular sheet whose dimensions are 45 and 24, and it is to be made into the shape of a cardboard, right? Sorry, in the shape of a cuboid, right? By cutting squares from its ends, cutting 4 squares from each corners and then folding it. Now let me show you how does it appear in the beginning. Like say, if we have this rectangular sheet of paper like this. Now, from the corners, these corners are cut, right? So on cutting these corners, let's say if I cut these corners, after cutting, it should appear like this. It should appear like this. And you can see that as of now, I've taken the edge to be cut, the edge of the square that we have cut from here, I've taken X. So we can see that the original length, which was beginning, it was 45. Now the length of this cuboid portion, that means after trimming it, once again, I'll show you that we had this whole length was given as 45, and we are cutting X from this side and X unit from this side. So therefore, the effective length of this cuboid is 45 minus 2x, and so will be the effective length of the width, which should be 24 minus 2x, because the original length was, originally it was 24, and we are trimming X from this side and X from this side, right? So after cutting this, it will appear like a cuboid with an, or tray with a, which is open box, we can say, whose dimensions, that is, whose length is going to be 45 minus 2x, whose breadth is going to be 24 minus 2x. And as I said, this being the height, this is the height, which is nothing but this corner, that is x. So we can say whose height is x. Now check what we have to find out here is to maximize the area. If you read it further, he said, what should be the question here is, what should be the side of the square? That means x is what we have to determine here. X is what we have to determine so that the area is maximum. That means we have to, not area, sorry, volume. We have to maximize the volume. Now let's say if I ask you what is the volume of a cuboid, it is clearly length into breadth into height. So I can do it from here. We know that the volume is L into B into H for a cuboid. So it should be 45 minus 2x, and then breadth, which is 24 minus 2x, and height being x. Height is x. Now we'll apply distributive property and we'll obtain the volume here. So we'll do 45 into 24. That comes out to be 1080. And then 45 into 2, that is minus 90x. And 2 into 24, that is 48x. And we have an x outside. Before that, we have to multiply this into this, that is, will give you minus 4x squared. Since I have to multiply with x, I can do it here only. If I multiply x with this x, so x squared, and this will turn into x cubed. Now, arranging them in the decreasing order of power, I'll get minus 4x cubed. And this is minus 138x squared. And plus 1080 times x. Well, this should be plus, right? Because 2 into 2 is 4. So this is 4x cubed. Now, once we have got the volume, we will find the derivative of this so as to find their extremes, that is the critical point. So if I find its derivative, this is v, so we can say that differentiating with respect to x, we are going to get dv by dx is equal to 4 into 3, that is 12x squared, minus 138 into 2 is 276x, and plus 1080 as the derivative of x is 1. Now we can find its second order derivative also, that is d square v by dx square. The second order derivative, that is 22 into 12, that is 24x minus 276 is the second order derivative. Now, after that, what we do, we compare the dv by dx with 0 in order to get the critical point. So we'll say that for maxima or minima, this dv by dx should be equal to 0. Now comparing this 12x square minus 276x plus 1080 with 0, I can see 12 is common. So this is x square. This is 23 times x, and this is 90 times equal to 0. Now from the factors of 90, we have to do middle term. So I'll write x square minus, this is 23, so this is minus 18x minus 5x plus 90 equal to 0. So what I did here is split 23 as 18 and 5. Now I can see that we have a x common from the first two terms, so that is x minus 18, and minus 5 common from the last, so that is x minus 18 again equal to 0. That means we'll get x is equal to 5 and x is equal to 18. Now you can see that assume if I take x as 18, and if you plug in 18 here, like 18, we are getting what? 24 minus 36. That means it's not possible, right? 24 minus 13 is a negative. So the width cannot be negative. That's why we will discard this value. So we'll say x is equal to 5. But then we have to show that the maximum, x is equal to 5 should give you the maximum value. That means by using second derivative test, we are going to do like this: d square v by dx square at x is equal to 5. Let's see if I plug in here 5, that is 24 into 5 is 120. This is 120 minus 276. That should give you minus 156. 156, which is what? Less than 0. So hence we'll say that this is maxima. We'll say that by second derivative test, right? This is second derivative test. We can say that x is equal to 5 is maxima. So we got x is equal to 5. Now let's say what will be the side of the square cut. We had to find the side of the square, and the side of the square which has to be cut here is 5 only. So we'll say that x is equal to 5 is the answer. We'll say x is equal to 5, and the unit has to be centimeter, is the required side of the square, so as to obtain the maximum volume. We don't have to find the dimensions of its length and breadth.